Good morning, Matthew Ward here with Ward Engineering. In this video, I'm going to give you my take on what I believe to be the most important concept in structural engineering. This is a principle that I use every day with my work, and I believe it's the underlying principle that really governs all of structural engineering. So here we got my son Caden. He's looking at one of my engineering books, trying to figure out which of these equations is the most important. It looks like his head's about to explode, so hopefully by the time this presentation is done, we'll be able to give them the answer. So here we go. So first of all, if you just take that question and type it into Google, this is what it says for the AI overview. It says the most crucial concept in structural engineering is ensuring structural stability and safety by understanding and managing the forces, loads, acting upon a structure and ensuring they are resisted by the structure's capacity. This involves meticulous analysis, design, and adherence to safety standards. So I really like this answer. I really agree with this answer. And my whole presentation was going to be based off of what this is actually saying. Now, so let's take this and let's unpack it on the next screen here. So if you take what that's saying right there and you break that down to its simplest form and do an equation or inequality here, it would look like this. It would just simply say capacity is greater than or equal to demand. It's really that simple. That's what this statement here is saying. And so I asked ChatGPT to make an image of a scale that's trying to illustrate that principle, and this is what it came out with. So on one side, you got capacity, which is this really heavy block over here. And then on the other side, you got demand, which looks like it's a bunch of these circular iron pieces or something. And so the capacity obviously outweighs the demand. So that's what this is trying to show. Now, I'm not super happy about this picture because like this plate really should be like really low down here, or this one should be higher. But in any sense, this is what it came up with. So if you can create an image that's better than this, I'll take it, put it in the comments. I'd love to see it. I didn't have any more time to put into trying to have it work on an image anymore for me. So there you go. That's what it's trying to say. Capacity greater than or equal to demand. And if you want to take that same statement and express it as a ratio, which is this is how I do it in my work most typically, is I'd put it as demand divided by capacity has to be less than or equal to 1.0. So in other words, like if you took the weight of this demand, divide it by however much this capacity weighs, that has to be less than 1.0. And we'll see this used in an example problem later on. So for me, I think that the most basic way to think about this is to think about it in terms of a checking account. So everybody understands a checking account. Everybody understands you can't spend more than what's in that checking account, ignoring credit cards or anything of that nature. So simply put, the account balance needs to equal or exceed the cost of the item. So in this case, C would be our account balance. That's your capacity. D is the cost of the item. That's the demand. So simply put, the balance in the checking account has to be greater than or equal to the cost. So if you want to buy the bike for $100, you need to have at least $100 in the checking account. It's really that simple. So this principle right here, which everyone understands, is actually the exact same principle that's being stated right here. The capacity of the structural member has to be greater than or equal to its demand. Same with a structural member, same with a checking account. It's the same principle. Okay, so what I read earlier, that was from ChatGPT. So let's read something that's straight from the code here. So this here is a statement from ASCE 716. It's arguably the most important structural document in the state of California for addressing loads on structures. So here's a statement straight from the code itself. So here's what it says. It says, structures, components, and foundations shall be designed so that their design strength equals or exceeds the effects of the factored loads in the following combinations. So let's take that and let's unpack that a little bit. So starting here, so that their design strength. So when you see the word design strength, you should be thinking of the word capacity. And then here where it says equals or exceeds, well, that would be equals or exceeds, which would be right here, capacity equals or exceeds the effects of the factored loads. And this statement, the effects of the factored loads, is another way of just saying the demand. So if you want to really just dial this straight down, it's saying the capacity needs to equal or exceed the demand, which is what I've already said multiple times. So for me, I would argue that this is perhaps the most important statement in all of structural engineering, and certainly the most important statement in this structural document, ASC 716. So obviously that checking account example and that capacity greater than equal to demand, that's very simple in theory. However, as I'm sure you can understand, that actually calculating any one side of that equation can be very, very difficult. So for instance, how do I calculate the capacity of an object? How do I calculate the demands on that object? Which code documents do I use? Should I use ASD or LRFD? Those are all very big questions, and they can be very confusing and complicated, and it could depend on, well, are we talking about wood or concrete or steel, and what's the application, etc., what state are you in, even maybe. So all of that can be very complicated, but the underlying principle is still straightforward. So just looking here, here's just a few equations that are used in this example that we're going to look at for how we calculated seismic demands on an air tank. So if we look here, this equation for FP, we see that FP involves an AP, an SDS, a WP, RP, IP, letter Z, and the letter H. And some of these have equations that drive that particular variable. Then down here you have maximums that it needs to meet, and then minimums it needs to meet. And then you come over here to this where EMH, where you now consider overstrength factors, where maybe we need to increase whatever demand by an overstrength factor. And then when we come over here to the right and look at these load combinations, well, we can't just consider seismic loads by themselves. We have to consider them acting with a certain amount of dead load or live load or snow load. And we can't just consider horizontal earthquake loads. We also have to consider vertical earthquake loads. So all of that to say that things can get very, very complicated very, very quickly. And this guy wants to pull his hair out of his head, which I can relate. Been there been there a lot of times, and it can be hard. So that's just a few pieces of what goes into. That's just the demand side of the equation too. That has nothing to do with, well, what's the capacity of the object. This is just going into demand. Okay, so here we are. We're going to look at an example. So this is a real life project I worked on about 2 years ago. It was designing the anchors for this tank. So this is an air tank for a high seismic zip code of California, 94588. And we designed the 4 anchors that anchor this tank to a concrete slab in a laboratory. So the weight of that tank was 1,671 pounds. It was 3.5 feet by 10 feet by 4 feet, and we used 4 5/8 inch diameter anchors to anchor it down, which we'll look at in a bit here. So I'm not going to do a complete overview of this tank. If you want to see how I designed it, I actually have that as an e-course on udemy.com. You can go there, you can pay to watch the course, and it's a complete walkthrough of how I designed the anchors. And that was a project. The fee for the project was $2,700, and I complete the whole project in real time in those videos in 1 hour and 15 minutes. So if you want to learn how to put your engineering skills to work and actually make money doing it, then the course is definitely for you. So I encourage you to go check it out. As well, in the course, I use 4 different templates. All 4 of those templates are for sale at wardeng.net, so you can buy those templates. Templates that I've put many, many hours into creating over the years, and now I use them to complete projects very efficiently. So here, this is just a screenshot from the structural calculations showing you the items that are in there. So most importantly, loads, seismic load being the most important. Then we designed the horizontal air receiver anchors. Then we designed the slab that it sits on. And so here's one screenshot from the structural calculations. So we're going to look here at this line that says steel strength. So under shear loads, steel strength, you'll see here where it says load, VUA in pounds, it says 380. So the shear load is 380 pounds, and that can think of that as demand. That's your demand column. And then over here it says capacity, phi VN, 6,668. So that's your capacity column. And then over here it says utilization. So this is the utilization ratio, or in other words, the demand to capacity ratio, like I talked about, D to C ratio. So it's taking those 2 values, dividing them, and coming up with 6. That's 6%. So 6%, that's very low. That's a very safe design, very conservative. Coming down here to pry out strength, same idea, taking these 2 numbers, dividing them, 6%. concrete edge failure and direction. Coming down here, 380 divided by 3473 is 11, so 11%. So all those checks come out good. And those are just a few of the checks. We use the Hilti software, and I think the Hilti pages, there's like 6 pages of Hilti calculations doing all these different checks for tension, shear, concrete, etc. So with our deliverables, we have two deliverables: our structural calculations, which we just looked at a few pieces of that, and then we have our plan sheet. So this here is a view of our 24 by 36 plan sheet, and we show all the information on here that the contractor would need in order to go build this job. So we show a picture of the tank. We have specifications from the Hilti anchors up here in the top left. We have a table up at the top which specifies the anchors, and then we have our notes for concrete, steel, etc. And then we have our foundation plan over here to the right. So the most important piece of information on this sheet is this anchorage schedule right here. So here we show that for anchoring that air tank to the slab, we're going to be using 4 of the 5/8 inch diameter Hilti QuickBolt TZ2s with a 3 1/4 inch embedment. And really, that's the basis of the project. That's what the contractor is looking for. Is what are the anchors that I'm going to use to anchor that air tank? And there it is right there. That's what the contractor will be using. So I'm just going to end here with a few final thoughts. So if you're early on in your engineering career, one of my biggest pieces of advice would be that you consider this principle in the context of your college courses. So for each college course, more or less, it emphasizes one particular side of the equation or the other, the capacity side or the demand side. So as you're taking your courses, always ask yourself, well, what is the purpose of this course? Is this course to help me understand the capacity side or the demand side? So for instance, if you think of the course statics, okay, statics is very much geared towards helping you understand the demands. So it's helping you consider, well, what's the demand reaction on this beam or this column or this footing, etc. Whereas if you look at mechanics of materials or material science, both of those courses, I would argue, are helping you better understand the capacity of some member. So always think like that. Keep that principle in the back of your head as you're in college, because I think that'll really help guide you in understanding like why you're actually taking that course or taking or learning in a particular equation or so. And then the next thing I would say here is you always know the first and last steps. Start there. So what that means to me is oftentimes I get a project where it's something that I've never done before, I've maybe never even thought about before, and now I have to do some type of engineering check to say this is good or it's not good. So when that comes up, I always keep in mind, well, I know the first step and I know the last step. So I always start there. So what I'll literally do is in my Word document, I'll type the word capacity, and then put a line, and then go down and type the word demand, and then go down and then type the word check, and then put capacity greater than demand. So what I'm doing is I'm giving myself a starting point by saying, okay, I know I need to calculate a capacity. I know I need to calculate a demand. And then at the end, I need to compare those two, and I need to be able to show that the capacity is greater than the demand. So that's where I always start. And yes, it may take me a few hours to even calculate what is the capacity of this thing. I don't know. I might have to do a lot of research and figure that out. And capacity of what? Capacity in tension or shear or bending or whatever? I don't know. But I need to figure out some kind of capacity. And then likewise, well, I need to figure out, well, what are the demands on this thing? I got to figure that out. But I know ultimately that's my direction. That's always what I need to do. Is figure out those two things independently and then compare them and show one greater than the other. So that's always the direction I know that I need to work in. And then I would also end by saying that I believe that this principle is arguably the most important principle in all of engineering, not only in structural engineering, but all of civil engineering in general. And I would even argue that in other fields of engineering. So, for instance, with sizing a water pipe, you're looking at, well, what are the demands on that water pipe, and then comparing them to, well, what's the capacity of that water pipe. Same with a sewer pipe. Well, what are the demands going to be, and what will the capacity of this pipe be? And same with an electrical panel. Okay, with an electrical panel, you're looking at, well, what will the electrical demands on this panel be, and does this panel have the capacity to meet those demands? So it's really an underlying principle that you're going to see everywhere in engineering. And I think the sooner you get it in your head and realize how important it is, the sooner you're going to see it show up everywhere. So there you go. That's all I have for you. Here's some contact information. Feel free to reach out to me if you have any questions. This is Caden. He's very happy now that he understands that the capacity has to be greater than demand, and that's the most important equation. He's a happy boy, so he can move on now. All right. Thank you. Have a good day. Bye.